This talk is about observational equality. Our story starts with Martin-Love type theory. MLTT is a sweet spot in the Curie-Howard correspondence between proofs and programs. On the one hand, it is expressive enough to do a large part of mathematics and to define a lot of computable functions. On the other hand, it is very tractable, which makes it a great foundation for proof assistance. It satisfies important properties such as decidability, normalization, and canonicity. However, the equality supplied by Martin-Love type theory is less than ideal. It encodes the equality of programs and not the equality of behaviors. Two consequences of this is that you don't get function extensionality and you don't get quotient types, but both are actually ubiquitous in mathematics. So, Altenkirch and McBride came up with observational type theory in the early 2000s to fix this. In OTT, the equality is not an inductive data structure. Instead, it is defined by recursion on the types and terms. For instance, if the user forms this equality, the system sees that it is dealing with functions, so the equality type computes to function extensionality, and this is how we obtain that property. Now, we will define our flavor of observational type theory as a simple extension of MLTT. The first cornerstone is elimination of the observational equality. Since it is not a data type, you cannot reason by pattern matching on it anymore. So how do we prove P of n if we know that n is observationally equal to m and we have P of m? Well, the answer is typecasting. We introduce a new primitive to do coercions between two observationally equal types. Now we can get our proof. Since we have function extensionality, we know that P of m is observationally equal to P of n, and we can cast our proof of P of m. But typecasting is a bit less powerful than pattern matching, because we can't use it to reason about the equality proofs themselves. We can circumvent this issue by making our observational equality proof irrelevant. Now, any two proof of observational equality will be convertible, which means the system can't tell them apart. Fortunately for us, proof-irrelevant types are already available in major proof assistants, so the work is already done here. Finally, we need one last piece of insight to handle inductive types. Regular inductive types, such as integers, dependent pairs, or lists, work just fine. However, indexed inductive types need a supplementary constructor. This is actually unavoidable, since we can get non-canonical inhabitants from function extensionality and typecasting. With all of this, we have an extension of MLTT that validates function extensionality. But now that we laid the groundwork, we can add more stuff, such as quotient types or subset types. And this concludes the brief summary of our flavor of observational type theory. So everything sounds good so far, but have we really not broken any of the properties of Martin-Love type theory? Surely this extension must have a cost, right? Well, we would argue that actually it does not. We used the Agda framework of Abel, Uman, and Vedzosi to prove that our version of observational type theory satisfies normalization, canonicity, and decidable conversion, just like Martin-Love type theory. And finally, the good news is that observational type theory is not too difficult to implement. All in all, we only need three ingredients: definitionally proof-irrelevant types, the primitives for cast and the observational equality, along with adequate rewriting rules, and a new constructor for indexed inductive types. As an experiment, we were able to use Jesper-Koch's rewrite rules to make a toy implementation in Agda. The next step is having it as an option in Koch. For more details, please come see our talk. It will be on Friday at 4 p.m. Thank you.